of the 2024 PT meeting is Eleonora De Giorgi. Sorry.
Yeah, it's fine.
Yeah. I made it up to the last name. Eleonora completed an integrated master's in chemical engineering with industrial study at the University of Birmingham. She spent the placement year with GSK and was working as part of the OSD PET team. She is now studying an engineering doctorate with the University of Birmingham and is in partnership with AstraZeneca, focusing on application of PET within the continuous tabletting process for low-dose formulations. It's a great last topic. Sorry to put you in this slot. Great to have you here. Stage is yours.
Thank you, Sebastian, for the introduction. And yeah, thank you for inviting me to speak here. So yeah, today won't be so much about low dose really, even though that's supposed to be the focus of my project. But I'll just show you a bit about optimizing PAT for the CDC process using the feed frame simulator and also the SentroPAT FO spectrometer. So it's still part of my project between University of Birmingham and, as we said, AstraZeneca. Right. It works, nice. So a bit about the contents. I'm going to be taking you through a bit of introduction about the NHD project and also how that aligns with the CDC process. Then the second part is going to be about optimizing the acquisition parameters for the SentroPAT FO spectrometer via the development of a small sort of app or GUI that I developed. And then the use of the feed frame simulator then to model the formulation. So basically applying this app with a small excipient case study. And then lastly, a bit of outlook in the future about comparing PAT solutions. That's going to be the next steps of my project. And then how to combine those with the feed frame simulator as well. Okay, so firstly, the introduction. So my project is mostly revolving around the continuous direct compression process. As you all know, you've heard all about this in the past 2 days. So the feeding, blending, and tableting sort of main steps. And it's about applying the process analytical technology sensors kind of throughout the process, basically, to ensure that we get the consistent product quality. And in terms of product quality, I mean like in terms of the tablets, and particularly about the API dose that's within them. So we're mostly actually interested in the feed frame, so the last stage here within the tableting sort of part of the process, because that's just before the product is formed. Therefore, it's quite a representative region for us to make decisions just before we get the actual product, and at that point it's too late, let's say. So the current PAT that is used at the moment, NIR spectroscopy is one of those, actually faces some challenges. We've already heard today when we approach sort of the limit of quantification. So that could be down to like low dose formulations such as 1% drug load, or maybe some with a low NIR response. So I'll be testing different PAT systems as part of my project and try to merge them and form a sort of optimized and consistent data analysis methodology so that we can then standardize our approach across the CDC lines. So from sort of our R&D labs to then the CDC lines. And yeah, the very ultimate long-term goal is to develop an integrated real-time release testing strategy, to then be able to do something like that. So then we can control the process, basically. Yep. So how does that align to the CDC then? So basically, we can start in the lab by developing models on the feed frame simulator at a sort of a much smaller scale, because the feed frame simulator, as we know from Phil and in the past 2 days as well, is very representative of the tablet press feed frame. So we can develop these models using a lot less material. So therefore we start with that. And then in the second phase, we remove some model offset and be able to like transfer the models and then apply them directly in line for the CDC process, basically. So that, yeah, the objective is, once again, to get that standard and optimized practice across the different processes and sites. So if we develop, for example, the model in site 1 with the feed frame simulator, then we can directly apply it in other sites where they have CDC lines. So, yeah. Okay, second part, about optimizing the acquisition parameters for the SentroPAT FO spectrometer. Right. Okay, there's a bit of maths here, but it's all basically known information, one here on the left. And basically, the way it works simply is that we have our NIR probe here, and it looks onto the powder bed, basically. We know the sample, the spot size here, because it's fixed at 5 millimeters. And then we also know that we have our feed frame here. This is a top view, and the paddles are spinning, so we know that basically for a given measurement time, the probe will be able to sweep a certain area of powder pretty much. And this is kind of what Steve was mentioning already in his talk yesterday. And we know that that measurement time is basically the integration time times the number of averages, so how many spectra we are collecting before getting one measurement. And once we know this area, we can estimate a sort of penetration depth of the signal here to then get a volume. And once we know this volume, with the density of our formulation, we can then estimate the mass that we're actually collecting with each measurement. So there's a list of parameters here that are important and that need to be known before we actually can do these calculations. But the ultimate aim, as many people have already mentioned, is to try and sort of align with capturing the mass equivalent of 1 unit dose or 1 tablet with each measurement, just to be representative, basically. So how would that work in practice? So firstly, we can optimize the actual intensity of our instrument by changing the integration time. So ideally, we achieve something between 40,000 and 50,000 counts. That's just to steer away from sort of the limit of detection, the saturation limit of the instrument, but also still get a quite high signal intensity, so we can maximize the potential for identification later. And then we input all the necessary parameters that I showed in the previous slide into the GUI or little app that I'll show in a second. And then we can calculate either the number of averages that we need to acquire the equivalent of a unit dose or tablet for each measurement, or we can also calculate the mass that we are currently acquiring with the given instrument settings that are already being used, for example. So it can be kind of used 2 ways. And then we want to check that the resulting measurement time is still approximately around a second or less, because we also don't want to decrease the frequency too much. Otherwise, we can't really do any real-time applications, because we still need to make that decision reasonably fast. And then this methodology can basically be repeated at different locations and for different like FO instruments at different sites to maintain that consistent and optimized method of acquisition. So basically, we can do it in our R&D lab, but also the CDC lines can do it themselves. And maintain that sort of same acquisition mass. And then, it's quite good to do it on web apps, because it can be widely available to everyone once it's uploaded on the website, basically. So there's no actual need to have MATLAB installed. So it's quite good. All right. So this is kind of what it looks like. It's still in development, so it's not completely finished. But essentially, I've made it a little bit easier here with like 2 different drop-down menus where you can put like the equipment that you're currently utilizing. So for example, the feed frame simulator or an actual feed frame of a tablet press, and also like the formulation of material. This is related to the density, and I mean, it can't be an exhaustive list, because obviously I can't list every single possible material formulation that people are going to use, but it does make it a little bit easier if it's one of the like known ones. Otherwise, obviously, it can be inserted manually. So this kind of density field becomes editable, and people can just input their own one. And in terms of the rest, it's kind of like common settings or geometry related parameters here that we can fill in. And then once those are all filled in, we can select what we want to do. So either calculate the averages or calculate the mass. And then by clicking this button or the other button when it appears, when this kind of switch is flicked, to calculate what we want. So for example, here, if we want to calculate the averages, we put in a target powder mass of, say, 1 tablet, and then the averages will appear. And at the same time, also the measurement time that's going to take, because we know that. So some next steps with this is basically just to collect some further information about the formulation bulk densities to just build a small database for that drop-down, but obviously can't be exhaustive, as we said, but that's fine. And then secondly, the only really parameters that is kind of like a rough estimation here is the penetration depth. As we've heard, that can be a difficult one to actually pinpoint down to a value because of the density changes and different conditions that change. So basically, I just wanted to try and do one myself. So I kind of designed this 3D printed sample holder by looking at literature of what has already been done to just try and estimate a little bit better that penetration depth. So this is what I ended up doing. So it's a very makeshift kind of solution here. I had to be a bit creative with the stands here and the clamps, but yeah. So I put the probe kind of upside down, filled the sample holder with powder, like made it flush with the top, and then it has like different sections with different depths, and then the probe was kind of like moved like above from section to section. I tried to make sure it was like level as well. There's a level here in the background you can see. But yeah, so basically I did it for 3 materials. I did it for MCC, mannitol, and lactose monohydrate. And then, yeah, as I said, made the powder flush with the top of the sample holder. However, there was a slight issue. As you can see here, this thing is not made of PLA, as I thought it was going to be, because I just gave it to some people to print for me, and I didn't really tell them what I was going to use it for. So they just gave it made of a semi-transparent resin, which with light applications isn't really ideal, as you can probably imagine. So yeah, basically didn't really have a clear spectrum. It was an artificially high absorbance, I guess, because all the light was kind of going through and then getting dispersed, so it wasn't really ideal for, well, yeah. So yeah, the only difference that I did notice, so if you see the spectrum here is just for MCC in this case. The blue line here at the bottom is just a pure MCC, so just literally looking at MCC powder. And then the top 4 lines that are kind of like overlapping with each other are the different depths when I tested it in there. There was one difference only with the 0.5 millimeters, the smallest depth, that was higher absorbance in this region and in this region as well. So that could indicate maybe that is a differentiating factor between the depths, so maybe the light was actually penetrating through to the sample holder. But again, I want to test it again with PLA, which is actually what the paper I read it from used. So if we go back to the paper, which is where this comes from, basically, it's in reflectance, so it's kind of opposite. But you can imagine that you can see different peaks here. So for PLA, 1 in this region and 2 more in that region there. And they can kind of be used, I suppose, when I redo it with PLA, because it's kind of flat here, so it matches quite well with the MCC, for example. So that will be like something to try again once I did get the PLA one printed, but it wasn't in time for this, so it will be done as a next step. Okay, so now how do we use this with the feed frame simulator, and how do we model formulations? So then I did a little experiment here with and the feed frame simulator and various blends. So I used it for, as we said, dynamic data collection, because it's a lot more representative. I'd made some simple blends of lactose monohydrate and MCC. And I made 3 batches of them, so I kind of repeated the same thing 3 times, just to have repeats. And then the lactose load changed from 10% all the way to like 75. I know it's artificially like very high, but I just wanted to show like the full range sort of very clearly. However, the 75 does have a little asterisk there, and that's because it didn't really flow very well. The lactose proved to have more issues than I anticipated, so therefore it's kind of been excluded from a lot of the analysis, because it just didn't really flow very well, and there were some issues, which I'll show later as well. But yeah, essentially what we did was just put the feed frame simulator on top of a table inside this downflow booth, so it's all like contained. And then here on the right, there's a bit of a zoomed in version. You can see the FO probe here, and then also we have this nice little collection attachment to the feed frame simulator, where we can put the powder back into the bottle, so there was no like powder sort of spillage everywhere and stuff like that. So that was quite nice. Okay, yeah. So if we go back to the app, then how we use this is basically we can input all of the parameters here on the right. So once we optimized the integration time, it turned out to be 14 milliseconds. So we put that one in. And then the estimated penetration depth, for now I've left it as 1. Obviously that might change later, but yeah. And yeah, the equipment I just obviously selected feed frame simulator, so the geometry kind of filled in there. The paddle speed was kept constant as 30 RPM. That was just an arbitrary sort of decision, so they could be other things depending on the process as well. And then the density was that as well. It was because it was kind of an average amongst different formulations. It didn't vary that much between the concentrations, so I kind of just kept the average for now. And then the output then, if we want to target a unit dose mass of 100 milligrams, then we put that in here. And if we click the calculate the number of averages, it comes up with 15. So that was what was used. And also the time for each measurement in that case is only 0.317 of a second. So it's just, there's also slight variation here based on the processing time. So it's, yeah, roughly that 100 milliseconds, but it does vary between measurements, and I've kind of taken an average from a previous experiment that I did and put that there. as a constant, but yeah, that's all. So then, once we figured out our optimal condition, we can then expand that range. So I started changing the number of averages and then trying to see if it has an effect on the noise and the model performance. So the constant, the paddle speed was kept constant, as we said, as that 30 RPM. And then I waited until the steady state was achieved before taking any NR measurements, basically, and then it took 20 data points per condition in the analysis. So then we can see here a table of the compiled results using like different number of averages and how much mass they would sample and what the measurement time was. So basically, if 15 here was our optimal conditions, I went like 3 below and then 3 like above that. And then the mass measured changed from 27% of a tablet mass to 319. So that's quite a wide range. And then also all these measurement times listed here, but they're all still below the second, so that's still quite good. Yeah. So initial pre-processing of the data. So basically I just changed some filters here, which looked like the optimal ones, let's say, or they're common ones that we actually use for our data analysis as well. So it was, yeah, first derivative, Savitzky-Golay, and then SMV. And on the right here, you can see like the spectrum once pre-processed, and there's a nice separation, especially in that region, like of the different concentrations, and you can see. Yep. So looking a bit more at the PCA and the score plots. So on the left one here, you can see all the data from all the concentrations here. And there's like 4 nicely identified clusters, especially in principal and component 1. So it captured 98% of the variability. So that's basically most of it. And then, yeah, there were just, if you look though on the right, I only isolated the data with 3 averages and 50 averages, so the 2 extremes, just to show this, basically, that the 3 averages data is a lot more like spread out, and a lot of it goes also outside of the model space, let's say, but a lot of the 50 data was all consistent and sort of, yeah, quite smoothed out in a way, so that was a good thing to notice. Yeah, if we then move on to the PLS models that I did, I used batches 1 and 2 as training sets, and then the third batch as validation sets. I did remove some wavelengths just to remove that noise at the edges, but yeah. And then the errors are like quite low, and you can see that it trends like quite well with the concentrations. It's a nice linear model with quite a high R squared of like 99. So yeah, and then the prediction was also similarly good with the third data set, the third batch. It matched quite well. So yeah, then I tried to further decrease the error. I tried to see, okay, what happens if I then remove that noisy 3 averages data, and what happens to the model? Same pre-processing, same sort of wavelength selection. And it did decrease a little bit. It only improved it, let's say, like quite marginally, say from 0.7 to like 0.68. So it's only a marginal improvement here, but it does show that it's by removing that sort of noisier data, it does improve the model a little bit. So yeah. Okay, and then also to just reiterate the point, basically, looking at a single wavelength and how the absorbance just changes, like the pure absorbance without doing anything on it, is basically I picked a like an 1430 nanometers. Obviously, that was an arbitrary decision. Other wavelengths did show the same like sort of behavior, but basically you can see the whole batch 1 run here from 10 to 75%, and towards the beginning of each run, there's low averages being used, like 3 is around this region, for example, and 50 is around this region. At the beginning, is a lot more noisy than towards the end of the run. So that just shows that like with 3, the data like jumps out quite a lot, whereas with 50, it's kind of smoothed down and a lot more consistent. And that happened like across all the runs. Also about midway was that point where we have the 15 averages, which was what was selected by the app, what was calculated by the app. So that's quite nice because it starts to converge around that point. So that's good. And then for 75 here, it was kind of inherently noisy. You can see it doesn't really stabilize too much. That's because it had some flowability and compaction issues when I put it in the feed frame simulator. I think the particle size of the lactose was very small, so it just caused some issues where there was a lot of bridging in here as well. You can't really see that, but there was a lot of bridging when I opened it up, and a lot of the powder didn't actually fill the chamber, as was for the other cases, where the powder actually fully filled the chamber, because we tried to sort of put a volume that was bigger than the chamber, so there was a bit of overflow here in the hopper just to make sure that it mimics a tablet press. But in this case, like there was bridging, a lot of the powder just kind of remained in the hopper and didn't really flow down to the chamber. So there was this kind of trench-like effect where it just stayed there and didn't really flow around the probe, so it wasn't really good. But yeah, so that's why I kind of deselect some of that from the analysis. Okay, so now just the final bit about what's going to happen next for the project, some future developments, and what I'm going to be looking at next. So, yeah, there's first of all a comparison between a different PAT technology here. We wanted this to be a general meeting, not a user meeting, so we're talking about Raman now. No, basically two different Raman spectrometers. The Anderson-Hauser with the RxM20 probe, and also a Tornado with the Hudson probe, just to check which of these two has better sensitivity for the compounds that we're going to be looking at. And that's going to be done just as a simple static analysis, sort of just in a powder cabinet with the appropriate shielding, of course. Because of the lasers, but yeah. And then once the optimal one's been determined from these two, we can then compare it to some other PAT systems, including the current SentroPAT FO NIR. So, and we can do that also dynamically, because it's a lot more representative, as we already said, but also the feed frame simulator, as you probably heard from Phil many times, it's got multiple probe integration, so you can actually test both at the same time to have some simultaneous comparison, and then also it can be used to transfer a model, so it's quite good as a system. Okay. Some conclusions. Yeah, there's just that need, I guess, within AZ as well to just streamline real-time release testing and trying to develop these strategies to align development work as well with the CDC lines and sort of the production environment, because we do want that flow of methodologies. And then I created this simple user-friendly tool to easily optimize the acquisition parameters of the SentroPAT FO, and also to maintain that consistency between the different environments, the lab and production as well. And then this can also be extended to, for example, other instruments such as the Raman, just to have that flexibility between the two, and just really make the tool a very versatile one as well. And then, yeah, the study on the optimal number of averages does highlight that there's a balance between the mass sampled with each measurement and also the number of averages, because as we saw before, if we increase the number of averages, yes, we get smoother, more consistent data. But obviously we have to make sure that we don't really sample more than the unit dose, or that our measurement takes too long. Otherwise, yeah, we just start running into other issues. So basically it's a balance that needs to be found. And also, yeah, just the upcoming studies, then we'll be looking at comparing other PAT technologies such as Raman to then determine what is the optimal method in terms of that sensitivity for the AZ formulations, which could be different. I mean, maybe NIR is optimal for certain ones and Raman is optimal for other ones, because they're all different. So, yeah. And that's it. I would like to acknowledge, that just people at AZ, my supervisors over at AZ and University of Birmingham, and everyone else I've worked with at AZ. So, yeah. But thank you if you have any questions.
Thank you, Eleonora. Maybe I should start walking in from the break.
Thanks for the very nice talk. I was curious about why did you fix the integration time at 14 milliseconds? Because then it sort of forced you to, that's quite a long integration time, and then it forced you to have a low number of averages. Whereas if you had decreased integration time, you could have benefited from more averages and noise averaging.
Yeah, so that optimization was kind of done based on the intensity of the actual signal. So if you look in the spectrometer, you can actually calculate the intensity that you take for each measurement. So that was optimizing based on the number of counts, so that intensity of the signal. That's just to maximize the intensity of that signal. But I mean, it could be an interesting avenue to just look at what if we do use a lower intensity and say we aim for a lower number of counts, but then we can use a higher number of averages. That could be an interesting thing to look at, actually. So, yeah, thanks. Yeah. Okay. Okay, that could be another. I didn't know about that, so that could be another avenue. Yeah. Thank you.
Just send me an email with the question. Any other questions? Adam?
Thanks for the great talk. I was curious, what kind of methodology are you going to actually use to compare between NIR and Raman?
Oh, yeah, haven't taught in too much detail yet about that, because that's coming next. But We were just thinking of literally optimizing the acquisition parameters for the separate instruments and just seeing what they can give us, basically, like at what point is our limit of detection, where can we look at it, for example, in terms of low doses as well, because that's where it's heading, right? So just maybe look at different low doses and just see how much we can identify with the two technologies kind of optimized for their own, their own settings, their own working principles, and then just seeing via like models and things like that where we can get that maximum detection, really. So I think roughly that way, but yes. No worries.
Any last question?
So in my experience, the NIR will give you fast results, really suitable for the feed frame. Raman will give you maybe some impurity results, but maybe those could be taken earlier in the process, not necessarily in the feed frame, because the number of impurities is probably not going to change. But maybe that can be covered as well in your studies.
Yes, perhaps we are looking at different technologies, and possibly, I can't say I'm really going to focus on other points along the CDC process in terms of where we put our PAT, but other people are looking at that, and yeah, that could be an avenue, I think, yeah, to just change the point maybe, or to combine them even. I mean, I said that I was going to do them both at the same time. It might be that we do go for both and then have the maximum amount of information, let's say, but yeah. Thank you, though, yeah.
Thank you, Eleonora. And with this last thanks to our speaker on stage, we are getting pretty close to the end, which makes me a bit sad. Believe it or not, it makes me more happy than sad. The shop is done, and I myself, I'm done as well. Just going for a short reminder to be put on here. Yeah, you may have noticed that I enjoyed to be session chair also for multiple sessions. It was a pleasure for me to introduce all these nice speakers, to get interesting questions running around, even in the corner of pain we had yesterday in the evening. At this point, I would like to say thank you to all participants, and I would ask all speakers from yesterday and today, which are still here, to come on stage for a last time. Also, Hubertus, you come up here as well, and then I hand over the microphone to Uwe. He gave it to me yesterday.
Yeah, also big thank you to all of you being with us the last days. It was a real pleasure to have you here. We enjoyed it so much. You probably have got this impression as well. So we want to thank you, everyone, for also contributing to us. And Sebastian, hey, speakers, coming, please, speakers. Otherwise, I wouldn't know what to talk anymore, and so I'm running out of words. Then. So I showed yesterday one of the pictures 10 years ago or 11 years ago with our speakers 11 years ago. So it's, maybe, Sebastian already takes care of that. And Sebastian, hey, come on. Should I help you with carrying? So, okay, I put the mic down and...
It's a little, very seasonal thank you that are stars which are popular at Christmas time, which are handcrafted in a small city about 60 kilometers to the east. We hope they will find a nice place in your homes and give you a nice life during Christmas, big Christmas time, and thank you.
This time we need to put the electronics together ourselves.
Yeah, just realized that. It's prepared for you, Matters, it's just wiring.
Okay.
And you do not even need to take care of plus and minus, just plug it in. So. Hans is going to Australia. Yeah. Don't travel.
Thanks again.
With this, the meeting is closed. We invite you to come back in a few years.